Hello everybody, my name is Alireza Shamsafar and today I'm going to talk about millimeter wave and sub-millimeter wave device characterization and modelings, and we'll talk about some practical tips for the measurements and verification as well. In this presentation we will see about millimeter wave, what is millimeter wave, what is the millimeter wave application, and specifically we will look at the millimeter wave application for 5G, and then we will see what 5G millimeter wave systems is and what is the requirements for that. Then we will look at the differences between and design challenges between the millimeter wave and sub-6 gigahertz. And then we will look more closely to the active and passive devices, starting from the process selection, passive modeling, or active modeling as well. At the end, we will look at the model verification and measurements. We will have some practical tips for modeling, and at the end, I will show some design example based on the developed model. What is millimeter wave? Millimeter wave is the wave that wavelength is in the millimetric range, millimetric scale, which means theoretically from 30 gigahertz up to 300 gigahertz. But due to some application for 5G and also some radar application for satellite, currently everything above 20 gigahertz, we call it millimeter wave. There are several applications for millimeter wave, and recently it's rising due to the higher bandwidth and high data throughput that millimeter wave provide, like optical drivers, very wide band range, it can go up to 110 gigahertz, or advanced 5G base stations, millimeter wave base stations at 28 gigahertz and 39 gigahertz, or CPU the same. Backhaul for microwave links can be even up to D band or E band. Radar terminal different frequencies, W band or V band, and traffic radar or automotive radar at 28 and 24 gigahertz and 77 gigahertz, and even SATCOM telecommunication, which it's used 20 and 30 recent one, or Wi-Fi 6. If we look more closely on 5G millimeter wave, which is more wide than other application, and it's going to be deployed globally, it had some certain requirements. As you see, there are a lot of scenarios and a lot of proposal on the systems, like digital beamforming, IF beamforming, hybrid beamforming, analog beamforming, multi-channel application, single or hybrid application, like two technology in one package, and so on. But there is one thing that is common with all of them, which they need best performance PA, LNA, and switch, or let's call it analog front end. Okay, now let's have a look on millimeter wave designs and challenge versus the traditional sub-6 gigahertz. As you know, sub-6 gigahertz, if you see the sub-6 gigahertz systems, you will see the graphs or the pictures like this in the left, like this pallets, high power transistors, a lot of bond wires, LDMOS or high power mimics, large PCBs, large connectors, and as you move to the millimeter wave domain, the power levels reduce and the integration level is higher. You see this multi-channel solutions, analog front ends. Higher integration level means that there is LNA, PA, vector modulator, or sometimes even the switches integrated, or power dividers, and mixer even. And also the packages are smaller, like ball grid array package or QFN, but high frequency LTCC packaging as well is deployed in the millimeter wave. This shows the clear difference between the millimeter wave and sub-6. On the other hand, as it's visible here, the loss over air in the millimeter wave is far higher than the sub-6 gigahertz. This requires this brings another challenge from the design, that your design need to have a good IRIP. For this reason, the beamforming scenarios are planned to be used for millimeter wave, and it makes sense to use that. However, there are a lot of other challenges in the design of millimeter wave, which is I listed here, like packaging, connector and testing, thermal quality. Millimeter wave need to be cheap as well. Currently, the solutions are very expensive if they want to use in the high volume. Calibration is difficult and is sensitive. And if we change it to the design issue, actually want to know what is the challenge there, it is the modeling issue. Accurate design kit model for passive and active device still is not available, especially for 3.5 technologies. This is always the modeling case. And even for the packaging or PCBs that we use, like LPCC and so on, dielectric loss of dispersion is not accurate at high frequency and need intensive or very accurate 2D or even 3D simulation. Here it's going to give an example. This is a design that it's multi-channel transceiver, moving transition to the antenna. Is designed to be 50 ohm based on the theory base, and as you see here, even theory based design works fine at sub-6 gigahertz. But look at millimeter wave, which we'll see complete disaster in terms of the matching. This shows how the design can be sensitive, and the EM simulation and optimization is needed for higher frequency. A part of that, if we look also on the PA side, or the amplifier side, typically at sub-6 GHz, the key is the efficiency, linearity, power, and gain. In millimeter wave, we need all this, plus more gain, more linearity due to the lack of the DPD, better noise figure, and higher level of integration. Okay, to have a good system or good design, we need also to select the right process. Currently, at the moment, there are a lot of options and the choices in both silicon and 3.5 technology that offer a good performance over millimeter wave. But depend of the application and depend of the parameter, the selection of the process can be quite challenging. And each process selection will lead to different model requirements. For example, I listed here some advanced technology in gallium arsenide and gallium nitride. And as you can see, even if we choose 100 nanometer gallium arsenide as advanced, with in two cases of the two different wafer thicknesses, we can come with 5 options with different wafer thickness and different protection layer in the top or pillars, which had direct effect on the models and the simulation environment. It means that we cannot use the same model that is developed for option 1, for example, for option 2 or option 3. And each of them require dedicated model and dedicated EM simulation environment for the development. Okay, we have passive modeling. It's a strange word, passive modeling. What does it mean? It means that we need to have models for passive for a designer to have a prediction of the performance in the schematic level, which can be later verified and capture the effect of the coupling and other effect with the EM simulation. And to do this, we need to define or modify the right substrate. We need to be very careful in the EM simulation setting with millimeter wave. It's very sensitive. This can be considered as a mesh frequency, port position, port types, and the calibration that we are applying on the ports. And more important is the time of simulation. Considering that you want to design a PA at 30 gigahertz, then if you consider To capture the third harmonic, then EM simulation need to be done up to even 100 gigahertz. And for some big structures, this can be takes weeks, and it can be completely block your simulation. To overcome this type of issue, one of the solution is substrate modification. Here I give an example of the shortest stop, which you can see here in the case of 1, 2. The port 1 and port 2 is the 2 ports of the stop. We use the full stack of the foundry. It means that all the details are there. Then in 2 step we modified it in a smart way to keep the simulation result the same. As you see here, the admittance parameter, they are exactly the same. The difference is few, but the simulation time dropped from 5 hours to 20 minutes for this simplified setup. About the active, as you know, we have 3 devices: switch, LNA, and PA, and each of them require a different model, different accurate model. Linear model for mainly for low noise amplifier, or eventually for driver amplifiers. We will need non-linear model mainly for power amplifier to capture the non-linearity, and we also have the switch model, which need to capture the impedances and also the losses for 2 states of the switch. The process, there are several processes and way to extract the model. I proposed here a straight way and very generic way of model extraction, which is more robust and doesn't require a lot of iteration. Actually, started with the DCIB measurements. This can be very straightforward. Only matter is that for silicon technology and gallium arsenide, it's fine. For GaN devices, due to the trapping and thermals, you need to be careful which type of the measurements you are doing and what you will get. Then we will do the S-part for multi-bias. This needs to be done as wide as possible in terms of the frequency and also in terms of the bias, because this information later we will use to extract the parasitic and synthesis. Then low frequency, low pull. What I mean low frequency means that the frequency needs to go so low that the parasitics or extrinsics will not play a role, and then you can really see the non-linearity of the device at the core of the device at the lower frequency. Then we will do the mid frequency or high frequency load pull, which will help us to understand the performance of the device. And since we did in the previous step the low frequency load pull, then we can distinguish the parasitics and the intrinsic of the device. You need to be aware that extrinsic, actually the parasitic, must be bias and power independent. They must come just from the device itself. And then based on that, we extrapolate the nonlinear behavior and build up the model and verify if our model is good or not. I give some examples of the measurements. This is a double pulse S-parameter measurement. This double pulse is used mainly for gallium nitride device to capture the effect of the trapping and also having a control, full control of the pulse chronogram. As you can see here, we can with advanced setups, we can put a right proper timing between 2 pulses to capture different effects, turning on the device or trap or detrap the surface traps, and then we can do the measurements up to very high frequency. Here I put the example up to 40 gigahertz. The second step is the low pull at higher frequency, mid frequency or high frequency. Here I show you the two examples of the max power and max efficiency of the GAN devices at 32 gigahertz, which show that it's with good accuracy we can capture the point. But you need to be very careful that as we are moving higher frequency, the local it became more challenging and challenging due to the nature of the losses of the cables, losses of the probes, mismatch, and so on. The dynamic range or the rotation of the impedances in the Smith chart can be limited. But there are a lot of new features and new advanced load pull system that trying to address this issue. And based on that, we also can select the load impedances in different state, and also we can monitor the time domain measurements, which can be extremely helpful to understand about the location of impedance, load lines, any distortion, and the current and voltage, to see that this information will help us in analyzing our model in the time domain, especially for the modulated signal. Later running modulated signal analysis, this data can be useful because the model needs to support that type of the simulation as well. Okay, for having a good model, as I mentioned, the key is having accurate measurements. To have accurate measurements, we need to have a good calibration and having a very good model verification. Typically, we have two options of measurements with the probes. No, two calibration with the probes. One is using the calibration of the probe tips to the probe tips, which is straightforward using the standard cal kit. And this typically is good if you measure the PA, LNA when the pad is there. But this is not accurate for the model. I will come to that. The second option is using on-chip calibration standard. They are not accurate for the old block like PA-LNA, since you are embedding the pads as well. But they are very good and accurate for the modeling. Here you see the set of the calibration like line, load, true, short, and there are several methods like TRL, LRM, and SALT. As you see, SALT is limited to the lower frequency, and TRL, multi-line TRL, can cover a very wide range of the frequency from almost 10 gigahertz up to 145 gigahertz, which is widely used for millimeter. Why calibration plane is important, or the reference plane is important? It's visible here. If you use the calibrations from the cal standards or standard calibration, you will have the probe tips as a reference plane for your calibration, which is this blue line. And if you use on-chip cal standards that you design in the same wafer with the same characteristic, you will bring the reference plane to the red line. This distance seems not big, but can have a huge impact in millimeter wave, and especially higher frequency and under different loads. As you see here, under 50 ohm, there is some difference, but it's not so visible, the difference between these two. But as you go far from 50 ohm and you go to the non-50 ohm, for example, here I don't remember it, 10 ohm condition, call it correctly, you will see that they start to show totally different behavior. For this reason, for modeling, is very important to capture the reference plane as close as the drain and the gate of the device. The model also needs to be wideband. Here I give an examples of realized model of a small device, 4x75 in gallium nitride, which the model can predict the performance of the device almost from 500 megahertz up to 110 gigahertz, and the fittings are very well, you can see. And moreover, the extrinsic and the intrinsic parameters that you see here need to have a physical meaning. It means that you can have this fitting, but these numbers need to have dimensionally reasonable dimensions to have a feeling that this device that you are using it can predict or extrapolate for other bias condition or in the outside of this frequency range. There is another example that I put here. Typically for Doherty power amplifier, we don't need only in class AB, but also sometimes we need good accurate in class C model, which is quite challenging for 3.5 technology. And here I want to emphasize the differences between the measured results, the model provided by the foundry as a PDK model, and the improved model. Typical behavior of the model is visible with the brown. As you see, it's far from the measurements, since the model typically developed for the class AB. And we improve the model to fit with the measurement as much as possible, also in class C, because as I mentioned previously in the SPAR multi-bias SPAR condition, your model need to satisfy the conditions versus different bias scenarios as well. There are some tips and practical points that can help you during the measurements or during the modeling. Accurate measurements is the key for the modeling. Designing a good launcher, especially for on vapor calibration, is the key. Launcher means the GSG structure or coplanar to the microstrip transition, and this, if it's designed well, it can increase your dynamic range. Landing position of GSG probe can be critical at higher frequency, especially over 100 gigahertz. This can lead to some phase and amplitude difference in the measurements. Placing the small opening on the ground of the GSGs, it can secure the same landing for the probe. As I mentioned previously, model parameter must have a physical reasonable, even if they fit very well with the measurements. The condition of the model need to be the same as much as possible like the final application of the device. Like, for example, if you want to use the device at room temperature under certain excitation, the model need to be verified and need to be predict the performance at the same temperature and same excitation. Instability or oscillation during the measurements can cause some odd values for model. It's suggested to when you are doing load pull or SPAR, not only extract the data, but also you monitor what you are measuring. If you see some instability or some oscillation, it can cause uncertainty on the model. And at the end, interpolation is always safer than extrapolation for a model. I want to also give some words about the behavioral model. Behavioral model is suitable for some design, like processes that they are not mature and is under development, or single stage amplifier blocks. But there are some limitations in terms of accuracy. It's very difficult, or it is almost impossible to measure harmonics at millimeter wave, since the harmonics falling down. It's really high frequency, sometimes sub-millimeter wave. Because setups, it became very complex and it's very costly in terms of the money and also time. There is also uncertainty and inaccuracy at harmonics. On the other hand, ultra-wideband model could have some convergence issue on some simulation, like modulated signal or harmonic balance simulation. To really end, I give you some examples. This is the 2 LNA designed in the common source and cascode structure, common source common gate structure in gallium nitride technology, which you can see here. The blue curve is the measured result, and the red one is the simulation result. You see that the simulation, thanks to good model, can capture very well the performance from DC up to even 50 gigahertz. Similar story here on the right side for the common source common gate, which due to the common gate transistor here, it's even more challenging to have a good fitting with simulation with measurement, which is recently I saw better fittings on the papers around the workshops. But still, there are a lot of rooms to improve, especially in the for gallium nitride technology. We also realized the same process, the switch, SPD switch, absorptive switch, which you can see here as well. The simulation and the measurements fit very well over a very wide demand range. It's almost from DC up to 40 gigahertz. And this shows that with good model, you can reduce the design cycles and also increase the sustainability of the process. Thanks for your attention, and now session is open for a question.